Imagine you're staring into the vast darkness between galaxies, the quietest place you've ever seen. You'd expect nothing unusual, but then a pattern emerges, a perfect circle, not made of stars, not made of dust, but something invisible, gigantic, and unexplained. A cosmic circle tens of millions of light years across. No echo, no repeated pattern, no known source. No one, not even the most powerful telescopes on Earth, can explain how it formed. Tonight we're exploring one of the most mysterious phenomena ever discovered in the universe, a cosmic structure that shouldn't exist, yet it does. This is not science fiction, this is real. Scientists call them odd radio circles, and they might be telling us something radical about physics, space, and the unseen universe itself. In 2020, radio astronomers scanning the sky with powerful arrays like the Australian Square Kilometre Array Pathfinder, ASCAP, noticed something surprising. Hidden in the data were giant circular features, perfectly round rings of radio emission with no visible counterpart in optical or X-ray light. These structures are enormous. To put their scale in perspective, a single circle can span up to 7 degrees on the sky. That's roughly 14 times the diameter of the full moon. If one of these objects were nearby, it would stretch across half the sky. Yet despite their size, they're exceedingly faint and only appear in sensitive radio frequencies. They're called odd radio circles because they emit radio waves, they are circular, they have no corresponding visible object, their origin is unknown. Their discovery was not a single event, but a series of detections, repeated surprises emerging from sky surveys. And that raised a profound question. What could create such a large circular pattern in radio light with no visible structure? Before ORCs were found, astronomers didn't expect such objects to exist. Radio astronomy works by capturing wavelengths far longer than visible light. Normal optical telescopes look at wavelengths around 400 to 700 nanometers. Radio telescopes detect emissions from millimeters to meters, a completely different part of the electromagnetic spectrum. When researchers map the sky in radio frequencies, they are effectively listening to the universe, not just looking at it. Instruments like ASKAP use interferometry, where dozens of individual dishes act like a single giant telescope. This technique allows astronomers to measure intensity of radio emission, spatial structure, spectral characteristics. In the case of ORCs, something unusual stood out. These rings are not filled with radio sources like galaxies or quasars. Instead, they appear as smooth, circular shells of emission with nothing obvious inside. Typically, radio circles around galaxies are explained by supernova remnants, star-forming regions, or jets from active black holes. But ORCs don't fit any of these categories. They are too large for supernova remnants, too isolated for star-forming shells, too symmetrical for jet structures. In fact, their symmetry and brightness profiles suggest an expanding ring or spherical shell, which is physically intriguing. Size matters, especially in astrophysics. ORCs are not small cosmic curiosities. Their scales are immense. Astronomers estimate their diameters based on angular size, how large they appear on the sky, distance estimates based on redshift. For the known distances, the inferred diameter is on the order of 1 to 3 million light-years. In some cases, closer to 10 million light-years. To compare, note, the Milky Way's diameter is 100,000 light-years. The distance between our galaxy and the Andromeda galaxy is 2.5 million light-years. That means ORCs are giant structures, even by cosmic standards. What's even striking is that they are thin rims. The brightness peaks sharply at the edges. Inside the rim, emission drops like a balloon seen in cross-section, yet nothing inside emits many radio waves. This geometry adds to the mystery. Several hypotheses emerged. 1. Supermassive black hole explosions. One idea is that these rings are the aftermath of a massive energy release from a galaxy's central black hole. Some galaxies host active galactic nuclei, AGN, that release huge jets of energy. If an AGN had a sudden explosive outburst, it might produce a spherical shockwave of charged particles expanding into the intergalactic medium. This shockwave could emit synchrotron radiation, the radio waves we detect. However, most ORCs are too symmetrical and isolated to fit this scenario neatly, and their host galaxies appear relatively normal, not hyperactive. 2. Galactic mergers or collisions. Another theory considers galactic interactions. When galaxies collide, the resulting turbulence can produce ring-shaped shockwaves. In principle, this could emit radio waves detectable across millions of light years. Yet the known ORCs lack clear signs of recent collisions. Their host galaxies appear undisturbed, which challenges this explanation. In cases of unknown or exotic physics. A more speculative approach involves unknown physical mechanisms. Perhaps a form of dark matter interaction or cosmic string phenomenon is producing these structures. Cosmic strings are hypothetical one-dimensional defects in spacetime that could, in principle, warp matter and energy, producing circular emissions. At this stage, no hypothesis fully explains the ORCs. This makes them truly mysterious, not just an odd astronomical feature, but a potential hint at new physics. Why do physicists care so much? The existence of ORCs touches several fundamental areas. Intergalactic medium. ORCs seem to interact with the diffuse plasma between galaxies. The symmetry and sharp edges suggest a shock wave moving through nearly empty space, which is puzzling. Energy requirements. For a circle millions of light years across to emit detectable radio waves, enormous energy is needed, far more than typical supernovae or stellar explosions. This raises questions about how galaxies can transfer energy across such vast distances. Cosmic frequency mapping. ORCs are invisible in visible light. They appear only in radio wavelengths, meaning we might be missing many other massive structures simply because we aren't looking at the right frequencies. In short, ORCs suggest that the universe is more dynamic and structured than we thought, challenging both astrophysics and cosmology models.
Let's briefly explore the mechanism generating the radio waves. Most astrophysical radio emissions are produced via synchrotron radiation. High-speed electrons spiral around magnetic field lines, emitting photons in the radio spectrum. The intensity and spectrum depend on electron energy, magnetic field strength, and geometry. In ORCs, the bright ring edges suggest a thin shell of relativistic electrons. The interior has little to no emission, like a hollow bubble in 3D space. Such morphology is uncommon in other known galactic phenomena. Some calculations suggest that to produce the observed emission, the total energy involved could be equivalent to millions of supernovae exploding simultaneously if the energy source is distributed isotropically. This is why ORCs are not just visually odd, they imply extreme astrophysical processes we don't fully understand yet. Scientists are puzzled because the odd radio circles are not just anomalies in size or shape, they challenge the very understanding of energy distribution across cosmic distances. The rings imply a sudden release of energy on a scale that is almost unimaginable. If a typical galaxy produces a supernova, the energy disperses over thousands of light years. But here, we are seeing structures spanning millions of light years. This raises questions about how energy can propagate through the intergalactic medium, which is mostly an extremely tenuous plasma, nearly a vacuum compared to even the sparsest regions of our Milky Way. The thinness of the emission rims suggests that the mechanism producing them is extremely efficient, focusing the energy into precise shells rather than diffusing it broadly. Some physicists have proposed that dark matter could play a role in this. Dark matter is an invisible form of mass that makes up most of the matter in the universe, yet it does not interact with light directly. If the odd radio circles are somehow tracing the presence of dark matter or influenced by its gravitational effects, it could be evidence of interactions previously unconsidered. For example, if a dense concentration of dark matter suddenly shifted or collided with another dark matter structure, It might produce shock waves in the surrounding intergalactic plasma, accelerating electrons to near light speed and creating synchrotron radiation visible only in radio frequencies. This hypothesis is speculative, but it aligns with the scale, symmetry, and isolation observed in the circles.
Another provocative idea involves cosmic strings, which are hypothetical defects in the fabric of space-time left over from the early universe. These strings would be incredibly thin, but possess enormous mass energy. If one of these cosmic strings passed through a region of space, it could create a massive disturbance in both matter and electromagnetic fields, potentially generating rings of radio emission as the surrounding plasma responds to the sudden strain in spacetime. This would explain the perfect circular geometry in the lack of corresponding visible matter, as cosmic strings would not be visible through traditional optical telescopes. While no cosmic string has ever been confirmed, odd radio circles could be the first indirect evidence of their existence. Some researchers suggest that the energy for these circles could also come from phenomena we understand but rarely witness on such scales. For instance, a previously dormant supermassive black hole might undergo a rapid, transient burst, expelling a spherical shell of relativistic particles. As this shell moves through the low-density intergalactic medium, the interaction could produce synchrotron emission detectable as a ring. The problem is, in known cases of such outbursts, we usually see associated activity in the central galaxy, such as jets, flares, or optical disturbances, and the host galaxies of ORCs appear remarkably quiescent. This discrepancy deepens the mystery, as if nature has found a way to produce massive energy releases without leaving the usual astrophysical fingerprints. The symmetry of the rings also implies a uniform expansion, which is extremely difficult to achieve naturally. In a turbulent medium like intergalactic space, any asymmetry should distort the shape over millions of light years, yet the observed circles are nearly perfect. This raises questions about the physical conditions in the intergalactic medium. Are there unseen magnetic field structures guiding the expansion? Or are these circles evidence of some universal principle that enforces geometric regularity at cosmic scales? Such questions verge on the boundaries between observational astrophysics and fundamental physics, pushing scientists to reconsider assumptions about the homogeneity and isotropy of the universe. Interestingly, these circles might also teach us about particle acceleration in extreme conditions. In astrophysics, electrons accelerated to relativistic speeds emit synchrotron radiation, producing the radio waves we detect. But the scale of acceleration needed for ORCs suggests cosmic-scale particle accelerators operating far beyond the energies achievable in human-made accelerators like the Large Hadron Collider. This invites profound questions. Could intergalactic magnetic fields be far stronger or more organized than previously thought? Could these circles hint at unknown mechanisms for distributing energy across the cosmos efficiently? Another compelling aspect is the apparent youth of these structures. Based on estimates of expansion speeds and the size of the rings, the odd radio circles might have formed relatively recently in cosmic terms, perhaps tens of millions of years ago. For astronomers, this is a blink of an eye. That a structure of this magnitude could form so recently and seemingly vanish without leaving traditional optical traces challenges the idea that massive cosmic structures take billions of years to evolve. If these phenomena are fleeting, it might explain why they were only discovered in the past few years with sensitive radio surveys, implying that more ORCs exist but have already dissipated, waiting to be detected by next-generation instruments. The discovery of ORCs also forces astronomers to rethink survey strategies. Traditionally, the universe has been mapped primarily using optical and infrared light, and only recently has radio astronomy reached the sensitivity required to detect such faint, extended structures. It is possible that these odd radio circles are just the tip of the iceberg, representing a population of previously invisible cosmic features that could reshape our understanding of galactic evolution, energy transfer, and the large-scale structure of the universe. This prospect excites both cosmologists and theoretical physicists, who may need to incorporate these phenomena into models of cosmic structure formation.
The physics governing these circles might also have implications for our understanding of cosmic expansion. If these structures are indeed spherical shock waves, their dynamics could provide indirect measurements of the density and pressure of intergalactic plasma, offering new insight into the distribution of baryonic matter in the universe. Most ordinary matter is believed to exist in diffuse forms between galaxies, but direct detection is challenging. Odd radio circles might serve as natural probes, revealing the physical properties of the medium they traverse. This could bridge observational astrophysics and fundamental cosmology in unprecedented ways. Perhaps most fascinating is the possibility that ORCs are a new class of astronomical phenomena entirely distinct from known galaxies, nebulae, or supernova remnants. They are mysterious not just because we don't know their source, but because they may represent physical processes or structures we have never observed before. For decades, astronomers assumed that all large-scale radio emissions had counterparts in optical or X-ray light. ORCs violate that expectation. If confirmed as a distinct phenomenon, they might constitute an entirely new chapter in cosmic physics, forcing us to ask questions about the nature of energy, matter, and the unseen scaffolding of the universe itself.
To understand how something like an odd radio circle could form, physicists start with the basic framework of plasma astrophysics. Most of the visible universe is not made of stars or planets, but of plasma, ionized gas where electrons and ions move freely. Even the vast spaces between galaxies contain extremely thin plasma, with densities sometimes as low as 1 particle per cubic meter. Despite being so sparse, this medium still responds to magnetic fields and shock waves. When a powerful event occurs in space, for example, an explosion, jet, or gravitational disturbance, the energy travels through this plasma as a shock wave. In classical physics, shock waves occur when an object or disturbance moves faster than the speed at which pressure information can travel through the medium. In the intergalactic medium, the speed is determined by the magnetosonic velocity, which depends on plasma density, temperature, and magnetic field strength. If an enormous burst of energy occurred at the center of a galaxy, it could drive a spherical shock outward. As the shock expands, it compresses the surrounding plasma and amplifies the magnetic field lines embedded in it. Charged particles trapped in these fields become accelerated through a process known as diffusive shock acceleration, sometimes called first-order Fermi acceleration. This mechanism is well studied in supernova remnants. Electrons bounce back and forth across the shock front, gaining energy each time they cross the boundary. Eventually, they reach relativistic speeds, meaning velocities close to the speed of light. When these relativistic electrons spiral around magnetic field lines, they emit synchrotron radiation, which appears primarily in the radio part of the electromagnetic spectrum. The same physics could theoretically operate on much larger scales. In the case of odd radio circles, the visible ring could represent the location where the shock wave is currently interacting most strongly with the surrounding intergalactic plasma. The interior of the sphere would be relatively empty of energetic electrons, which explains why the radio emission is strongest only along the edge. However, the scale of these structures introduces a serious energy problem. A supernova releases roughly 10 to the 44th joules of energy. Even the most powerful gamma-ray bursts release around 10 to the 47th joules, but producing a shock wave spanning millions of light-years would require energies many orders of magnitude greater. Some theoretical estimates suggest the required energy could approach 10 to the 53rd to 10 to the 55th joules, depending on the density of the surrounding medium. For comparison, the total energy output of our Sun over its entire 10 billion-year lifetime is about 10 to the 44th joules. That means the event responsible for an ORC might release billions of times more energy than a star produces in its entire lifetime. Where could such energy come from? One candidate mechanism involves supermassive black hole feedback. Most galaxies contain black holes at their centers with masses millions or billions of times larger than the Sun. When matter falls into these black holes, gravitational potential energy is converted into radiation and kinetic energy. In some cases, this produces enormous relativistic jets that extend thousands of light-years into space. These jets are powered by a combination of accretion disk physics and magnetic field interactions described by the Blandford-Znaiec mechanism, where rotational energy is extracted from the black hole through magnetic fields anchored in the accretion disk. The resulting outflows can accelerate particles to extreme energies and inflate enormous lobes of plasma around galaxies. However, known jet structures typically produce elongated shapes, not perfect circles. For an ORC to form, the energy would need to be released isotropically, meaning roughly equally in all directions. That would require a very different configuration than the narrow jets normally associated with active galactic nuclei. Another idea being explored involves galactic-scale shock waves produced by starburst activity. When a galaxy undergoes a burst of intense star formation, thousands of massive stars form simultaneously. These stars live short lives and explode as supernovae within a few million years of each other. The combined effect of these explosions can drive powerful outflows called galactic winds. These winds push gas and magnetic fields outward from the galaxy, forming bubbles that expand into the surrounding medium. Over millions of years, the expanding shell could reach intergalactic scales, potentially producing radio emissions similar to what is observed in ORCs. Yet there are difficulties with this explanation as well. The host galaxies associated with some ORCs do not show strong evidence of recent starburst activity. Their stellar populations appear relatively ordinary, suggesting that if such an event occurred, it must have happened tens of millions of years ago and has since faded from optical view. Because of these challenges, some physicists have begun considering more exotic possibilities involving the large-scale structure of the universe itself. On cosmological scales, matter is not distributed randomly. Galaxies form vast networks of filaments and clusters known as the cosmic web. Between these filaments lie enormous voids where matter density is extremely low. At the boundaries where filaments meet, gravitational forces compress gas and generate enormous shock fronts as matter flows into galaxy clusters. Computer simulations of cosmic structure formation show that these shocks can accelerate particles and produce radio emission across enormous distances. In principle, an ORC could represent a cross-section of such a shock wave observed from a particular angle. But simulations suggest that cosmic web shocks should appear irregular and filamentary rather than perfectly circular. The remarkable symmetry of ORCs therefore remains difficult to reproduce in theoretical models.
Another intriguing line of thought involves cosmic magnetism. Magnetic fields exist throughout the universe, but their origin is still not fully understood. Some theories suggest that primordial magnetic fields were generated during the early universe, possibly during phase transitions shortly after the Big Bang. If large-scale magnetic structures exist in intergalactic space, they could channel energetic particles along curved paths. Under the right conditions, this might produce ring-like synchrotron emission when particles encounter regions of enhanced magnetic field strength. Testing such theories requires extremely sensitive measurements of radio polarization, which can reveal the orientation of magnetic fields in distant structures. Future radio surveys with instruments like the Square Kilometre Array are expected to provide much more detailed polarization maps, which may help determine whether ORCs are shaped by magnetic processes. One of the most fascinating aspects of ORCs is how they illustrate the limits of our observational capabilities. For most of the 20th century, astronomers relied primarily on optical telescopes. The radio sky remained largely unexplored until the development of large interferometric arrays in the late 20th and early 21st centuries. The discovery of ORCs occurred during a large survey called EMU, the Evolutionary Map of the Universe, conducted with ASCAP. This survey aims to catalog tens of millions of radio sources across the sky. When the first ORCs appeared in the data, astronomers initially suspected they might be artifacts of the imaging process. Radio interferometry is complex, and sometimes circular patterns can appear due to calibration errors or processing glitches. To rule this out, the objects were re-observed using independent instruments, including the Meerkat radio telescope in South Africa. The rings appeared again, confirming that they were genuine astrophysical structures. As of now, astronomers have identified only a small number of confirmed ORCs. Their rarity makes them difficult to study statistically, but it also suggests they may represent brief or unusual cosmic events. If the structures expand and fade over time, we might only observe them during a relatively short window in their evolution.
That would mean the universe could be filled with many more ORCs that have already dissipated or are too faint to detect. This possibility highlights an important principle in astrophysics. What we observe is often only a fraction of what exists. Our view of the universe is limited by the sensitivity of our instruments and the wavelengths we choose to study. Odd radio circles remind scientists that entirely new classes of cosmic phenomena can remain hidden for decades simply because we were not looking in the right way. From a theoretical perspective, this discovery opens an opportunity. ORCs could become powerful laboratories for studying relativistic plasma physics, magnetic field amplification, and large-scale particle acceleration. These processes are extremely difficult to reproduce on Earth. Even the most advanced particle accelerators operate on scales measured in kilometers. ORCs, by contrast, represent natural accelerators spanning millions of light years, driven by energies far beyond anything humanity could generate. Understanding them could therefore shed light on fundamental questions about how the universe distributes energy, organizes matter, and evolves over cosmic time. And perhaps most intriguingly, the physics of ORCs might intersect with some of the deepest questions in cosmology, including the nature of dark matter, the evolution of galaxies, and the dynamics of the cosmic web itself. Imagine a sudden release of energy in a distant galaxy, an event so powerful that it launches a shock wave outward into the surrounding universe. At first, the expansion is extremely rapid. The initial energy compresses the surrounding plasma and magnetic fields, forming a moving shell. As the shell grows larger, it sweeps up more matter from the intergalactic medium, and its speed gradually decreases. Yet during the early phase of expansion, the shock wave can travel thousands of kilometers per second. To understand this process, astrophysicists use models similar to those developed for supernova explosions. One of the most famous is the Sedov-Taylor blast wave solution, originally derived to describe the expansion of an explosion into a uniform medium. In this framework, the radius of the expanding shock depends on the energy of the explosion, the density of the surrounding medium, and the time since the event occurred. While the original model was designed for stellar explosions, the underlying physics can scale up dramatically. If the explosion energy is large enough, the same mathematical behavior can describe structures millions of light years across. In the extremely low-density environment between galaxies, even a modest amount of injected energy can travel astonishing distances before dissipating. The intergalactic medium typically contains only a few particles per cubic meter, which means there is very little resistance to the expanding shell. As the shock wave moves outward, it compresses the plasma ahead of it and heats it to millions of degrees. At the same time, the magnetic fields embedded in the plasma become amplified, forming tangled structures along the boundary of the expanding shell. These magnetic fields play a crucial role in producing the radio emission we detect from structures like odd radio circle. Charged particles moving through magnetic fields experience a force that causes them to spiral along the field lines. When these particles reach relativistic speeds, their motion produces electromagnetic radiation. Because the particles are moving along curved paths, the radiation is emitted in the radio spectrum as synchrotron radiation. The brightness of this radiation depends on several physical factors. First is the density of relativistic electrons within the shock region. Second is the strength of the magnetic field. Third is the distribution of electron energies. In many astrophysical shocks, the energy distribution of electrons follows a power law, meaning there are many low-energy particles and progressively fewer high-energy ones. This distribution determines the spectral signature of the radio emission. Observations of odd radio circles show that their spectra are broadly consistent with synchrotron radiation, which strengthens the argument that they originate from shock-accelerated electrons. But there's an additional complication. The radio emission from these circles appears concentrated along a thin rim rather than filling the entire interior. That suggests the shock front itself is where the particle acceleration is occurring. As electrons gain energy at the shock boundary, they emit radiation briefly before losing energy through several processes. One of the most important is synchrotron cooling, where the same mechanism that produces the radiation also drains energy from the electrons. Another is inverse Compton scattering, in which energetic electrons collide with photons from the cosmic microwave background, transferring energy to the photons and reducing the electrons' kinetic energy. Because these cooling processes operate relatively quickly on cosmic timescales, the energetic electrons cannot travel far from the shock before losing their energy. The result is a bright rim of radio emissions surrounding a much fainter interior region. This geometry matches what astronomers observe in ORCs, suggesting that the shock front marks the boundary where particle acceleration is still active. One question scientists immediately ask is how such a shock could remain so perfectly circular. In most astrophysical environments, irregularities in the surrounding medium cause shock waves to distort as they expand. Differences in density or magnetic field strength should produce asymmetries in the shape of the shell. Yet the observed rings appear remarkably uniform, implying that the medium into which they are expanding is extremely smooth on very large scales. This observation may reveal something important about the intergalactic medium itself. Cosmological simulations indicate that gas between galaxies can become highly uniform in regions far from galaxy clusters. If an explosion occurred within such a region, the shock wave could expand symmetrically for millions of years without significant distortion. In other words, the near-perfect circular shape of an ORC might be telling us as much about the surrounding environment as it does about the explosion that created it. Another key factor in understanding these objects is the role of cosmic magnetic fields. Magnetic fields are present almost everywhere in the universe, but measuring them directly is difficult. Astronomers often infer their presence through the effects they produce on charged particles and electromagnetic radiation. In the case of radio emission, one useful tool is the measurement of polarization. Synchrotron radiation tends to be polarized, meaning the electric field of the emitted waves oscillates in a preferred direction related to the orientation of the magnetic field. By analyzing the polarization of the radio signal from an odd radio circle, astronomers can estimate the structure and strength of the magnetic fields within the shock region. Early observations suggest that the magnetic fields along the rims of these circles may be significantly amplified compared with the surrounding medium. Such amplification can occur naturally when shock waves compress the plasma and stretch the magnetic field lines. The resulting fields can be many times stronger than those present before the explosion occurred. If confirmed, this process would make ORCs valuable laboratories for studying magnetohydrodynamics, the physics that describes how magnetic fields interact with conducting fluids like plasma. Magnetohydrodynamic turbulence plays a major role in many astrophysical environments, from star-forming regions to galaxy clusters. Yet observing these processes directly is extremely challenging because they occur on scales far beyond human experience. Structures like ORCs may provide a rare opportunity to observe the evolution of magnetized shocks across intergalactic distances. The timing of these events is another important clue. Based on the estimated expansion speeds and the size of the rings, many researchers believe that ORCs may be roughly tens of millions of years old. In cosmic terms, this is relatively young. For comparison, the Milky Way galaxy is more than 13 billion years old. If the ORCs are indeed remnants of explosive events that occurred tens of millions of years ago, that means we are observing them during a brief stage of their evolution before they eventually fade into the background of the universe. Determining their age more precisely requires estimating how fast the shock wave is expanding. One way to approach this is by measuring the radio brightness profile across the ring. The width of the emitting region can reveal how quickly electrons are cooling after being accelerated at the shock front. Combining this information with models of synchrotron cooling allows scientists to estimate the magnetic field strength and the velocity of the expanding shell. Early studies suggest that the expansion speed may be several thousand kilometers per second, though the exact value remains uncertain. Another line of evidence comes from the galaxies located near the centers of some ORCs. In several cases, astronomers have identified a faint galaxy at the center of the circle, suggesting that the explosion might have originated there. These galaxies are often located billions of light years away, meaning the events that created the circles occurred long before life appeared on Earth. When the radio waves from these structures finally reached our planet, they carried with them a record of cosmic events that unfolded millions of years earlier. One particularly intriguing possibility is that these circles could be the relics of massive black hole outbursts that occurred when a galaxy suddenly began accreting matter at a high rate. During such episodes, the black hole can release enormous amounts of energy in a relatively short period of time. If the energy were distributed in all directions rather than concentrated into jets, it could produce a spherical shock wave expanding outward into intergalactic space. Another possibility involves galaxy mergers. When two galaxies collide, their central black holes may eventually merge as well, releasing gravitational energy that can disturb the surrounding gas. Such mergers are expected to generate powerful gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity and detected directly for the first time in 2015 by the LIGO scientific collaboration. Although the gravitational waves themselves pass through matter almost undisturbed, the violent dynamics of the merging galaxies could trigger enormous outflows of gas and plasma capable of producing expanding shock shells. Observations alone may eventually distinguish between these possibilities. If ORCs are caused by black hole activity, astronomers might find evidence of past accretion events in the host galaxies. If they are caused by galaxy mergers, the galaxies near the centers of the circles might show signs of disrupted structure or unusual stellar populations. Detailed observations with new telescopes will be crucial for testing these hypotheses. One of the most promising instruments for future discoveries is the Square Kilometer Array, a next-generation radio observatory currently under construction. When completed, it will be the largest radio telescope ever built, capable of detecting extremely faint radio signals across enormous distances. The SKA will survey the sky with unprecedented sensitivity, potentially revealing hundreds or even thousands of additional odd radio circles. If that happens, astronomers will finally have a large sample of these objects to analyze statistically. Patterns in their sizes, distances, and host galaxies could reveal the physical mechanism responsible for their formation. For now, each newly discovered ORC adds another piece to the puzzle, a cosmic fingerprint left behind by an event powerful enough to reshape space on a scale measured in millions of light years. The deeper scientists investigate these structures, the more they realize that they are probing a regime of physics that lies at the intersection of plasma dynamics, cosmology, and high-energy astrophysics. The rings themselves may be relatively simple in appearance, but the processes that created them could involve some of the most energetic and least understood phenomena in the universe. And perhaps the most exciting possibility is that odd radio circles are not just remnants of known astrophysical events. They might represent something entirely new, a new type of cosmic explosion or large-scale plasma instability that has never been observed before. If that is true, these faint rings of radio light could be the first hints of a phenomenon that forces scientists to revise their understanding of how energy and matter behave on the largest scales in the universe.
When physicists attempt to understand the deeper origin of structures like the odd radio circle, they often begin by studying the behavior of particles in extreme cosmic environments. In many astrophysical systems, the most energetic processes occur where matter and magnetic fields interact violently. These environments act as natural particle accelerators, capable of boosting electrons and protons to energies far beyond what can be achieved in laboratories on Earth. One of the most important acceleration mechanisms in astrophysics is known as diffusive shock acceleration. The idea is conceptually simple, but physically profound. Imagine a charged particle trapped between two regions of turbulent magnetic fields near a shock wave. Each time the particle crosses the shock boundary, it encounters magnetic irregularities that scatter it back and forth. Every crossing allows the particle to gain a small amount of energy from the motion of the shock itself. Over many crossings, the particle's energy increases dramatically, eventually reaching relativistic speeds. This mechanism is believed to operate in supernova remnants, galaxy cluster shocks, and possibly even near the boundaries of expanding ORCs. Because the electrons accelerated in this way move close to the speed of light, they emit strong synchrotron radiation as they spiral through magnetic fields. The radiation spectrum that results follows a characteristic power law distribution. When astronomers measure the radio spectrum of an object, the slope of that distribution, known as the spectral index, can reveal how the particles were accelerated and how quickly they are losing energy. Early measurements of ORC spectra indicate a spectral index consistent with synchrotron emission produced by shock acceleration. This is important because it suggests that the rings are not simply passive structures, but are actively accelerating particles. In other words, these objects may still be evolving, continuing to inject energy into the surrounding intergalactic medium long after the initial event that created them. Understanding how such large-scale acceleration could occur requires examining the environment in which these rings exist.
Most ORCs appear far from dense galaxy clusters, located instead in relatively isolated regions of the cosmic web. The cosmic web is the large-scale structure of the universe, consisting of filaments of galaxies separated by vast voids. Matter flows along these filaments under the influence of gravity, gradually building clusters of galaxies at the intersections. Where these flows collide, enormous shock fronts can form. These shocks are much larger than those produced by individual galaxies. In fact, simulations suggest that some cosmic web shocks may span tens of millions of light years. If an ORC happens to lie within such a region, the shock from a galactic outburst could interact with the larger scale structure of the cosmic web, amplifying the radio emission and shaping the expanding shell into the circular forms we observe. Another aspect of these structures that intrigue cosmologists is their potential connection to the missing baryon problem. According to models of the early universe, a certain amount of normal matter, known as baryonic matter, should exist today. This matter includes the protons and neutrons that make up stars, planets, and gas clouds. However, when astronomers add up all the baryonic matter they can observe directly, they find that a large fraction is missing. The leading explanation is that this missing matter exists in extremely hot, diffuse gas distributed along the filaments of the cosmic web. This gas is known as the warm-hot intergalactic medium, often abbreviated as WIM. Because the gas is so thin and hot, it emits very little light and is extremely difficult to detect directly. Shock waves associated with ORCs could provide a new way to study this hidden matter. As the expanding shell passes through the intergalactic medium, it compresses and heats the gas, potentially making it detectable through its radio emission or through subtle distortions in the cosmic microwave background radiation. If scientists can measure how the shock interacts with the surrounding gas, they may be able to estimate the density of the otherwise invisible baryonic matter. The cosmic microwave background itself plays an interesting role in these environments. This radiation, left over from the early universe, fills all of space with a faint glow at a temperature of about 2.7 Kelvin. Relativistic electrons produced in ORC shock fronts can scatter these microwave photons through a process called inverse Compton scattering. In this interaction, the electron transfers part of its energy to the photon, boosting the photon to much higher frequencies, such as X-rays. By comparing the radio emission produced by synchrotron radiation with the higher energy emission produced by inverse Compton scattering, astronomers can estimate the strength of magnetic fields inside the expanding shell. This comparison provides one of the few direct ways to measure magnetic field strengths in extremely distant cosmic environments. Magnetic fields themselves may hold part of the explanation for why these rings form so cleanly. In magnetized plasma, the motion of charged particles is strongly influenced by the orientation of magnetic field lines. If the magnetic field surrounding the originating galaxy were arranged in a roughly spherical pattern, perhaps shaped by earlier galactic winds, an expanding shock wave might naturally follow those field lines, maintaining a nearly circular shape as it propagates outward. This leads to another intriguing possibility. The rings could be remnants of multiple energetic events rather than a single explosion. Over millions of years, a galaxy might experience repeated episodes of black hole activity or bursts of star formation. Each event could push gas outward, gradually inflating a larger bubble in the surrounding intergalactic medium. Eventually, the outermost boundary of this bubble might appear as a radio ring when illuminated by fresh particle acceleration at the shock front. If this interpretation is correct, ORCs might represent the long-term ecological impact of galaxies on their environments. Rather than being isolated systems, galaxies could influence the structure of intergalactic space across distances millions of times larger than their own size. The energy released by processes occurring in galactic centers would then ripple outward through the cosmic web, shaping the distribution of matter on enormous scales. There is also a fascinating possibility that the symmetry of these rings could be linked to fundamental properties of the universe itself. On very large scales, cosmology assumes that the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and location. Structures like ORCs might serve as natural experiments testing this assumption. If the rings expand symmetrically over millions of light years, it suggests that the underlying environment is indeed very uniform, at least within those regions. However, if future observations revealed distortions or systematic alignments in the orientation of ORCs, it could hint at subtle anisotropies in the large-scale structure of the universe. Such findings would have implications for cosmological models describing how matter and energy evolved after the Big Bang. New radio telescopes are already beginning to push these investigations forward. The square-kilometer array, once fully operational, will be capable of mapping the radio sky with extraordinary sensitivity and resolution. This instrument will allow astronomers to detect faint radio shells that were previously invisible and to study their internal structures in detail. Another powerful facility contributing to this research is the Meerkat radio telescope, which has already produced some of the most detailed images of ORCs. Meerkat's observations revealed subtle variations in brightness around the rings, suggesting that the shock fronts may be interacting with uneven regions of intergalactic gas. Each new observation helps refine theoretical models, but it also raises new questions. Why are ORCs so rare? If powerful explosions in galaxies are relatively common, we might expect to see many more such structures. The fact that only a handful have been detected so far could mean that the conditions required to produce them are extremely specific. For example, the event might need to occur in a galaxy located in a particularly low-density region of the cosmic web. In denser environments, the shock wave could dissipate too quickly or become distorted by nearby structures. Alternatively, the phenomenon might require a precise alignment of magnetic fields that occurs only under rare circumstances. Another possibility is that ORCs evolve rapidly and become invisible after a relatively short period. Once the electrons responsible for the radio emission lose their energy, the structure would fade from radio surveys even though the expanding shell of gas continues moving outward silently. This idea suggests that the universe may contain many ancient ORCs that have already faded away, leaving behind enormous bubbles of disturbed intergalactic plasma. Detecting those relics might require observing different wavelengths or looking for subtle temperature variations in the surrounding gas. From a broader perspective, the discovery of ORCs illustrates how modern astronomy is entering an era of exploration driven by massive data sets. Large sky surveys produce enormous volumes of information, revealing faint structures that would have gone unnoticed in earlier observations. Sometimes the most important discoveries emerge not from targeted searches, but from unexpected patterns hidden within these vast data archives. Odd radio circles are a perfect example of this process. They were not predicted by theory and were not the primary target of the surveys that discovered them. Yet once they appeared in the data, they opened an entirely new line of investigation into the physics of large-scale cosmic explosions. And as astronomers continue scanning the radio sky with ever more sensitive instruments, the chances increase that even stranger phenomena will appear. Structures that challenge our current understanding of astrophysics just as profoundly as ORCs do today. One direction researchers have started exploring is whether odd radio circles might be connected to the dark matter halos surrounding galaxies. Every galaxy, including the Milky Way, sits inside an enormous halo of invisible matter that extends far beyond the visible stars. This substance, known as dark matter, interacts primarily through gravity and makes up roughly 85% of the matter in the universe. Although we cannot see it directly, its gravitational influence shapes the motion of galaxies and the large-scale structure of the cosmos. Dark matter halos are not small. A typical galaxy's halo can extend hundreds of thousands of light-years, sometimes even millions. Inside these halos, gas and plasma accumulate, forming an extended environment around galaxies that is far larger than the bright stellar disk. If a powerful event occurred at the center of a galaxy, perhaps involving a burst of energy from a supermassive black hole, the resulting shock wave would not expand into empty space immediately. Instead, it would first propagate through the galaxy's halo, interacting with gas trapped within the dark matter structure. As the shock moves outward, it could eventually reach the outer boundary of the halo, where the gas density drops sharply. At this boundary, the shock wave might suddenly accelerate and expand more freely into the surrounding intergalactic medium. This transition could produce a bright shell of synchrotron radiation as relativistic particles encounter new magnetic conditions. In such a scenario, the visible ring of an odd radio circle might mark the interface between a galaxy's halo and the larger cosmic environment.
This idea is attractive because it links ORCs to well-established features of cosmology. Dark matter halos are fundamental components of galaxy formation models, and their boundaries, sometimes called virial radii, represent regions where gravitational equilibrium changes. If ORCs trace these boundaries during energetic outbursts, they could become valuable tools for measuring halo sizes and studying how galaxies exchange energy with the intergalactic medium.
Another possibility under investigation involves repeated cycles of black hole activity. Observations show that supermassive black holes do not remain continuously active. Instead, they appear to switch between quiet periods and powerful outbursts as gas occasionally falls toward them. During active phases, enormous amounts of energy can be released in relatively short bursts. If a galaxy experienced several such episodes over millions of years, each outburst might launch a new shock wave expanding outward. Over time, these successive shells could travel through the same region of space, occasionally interacting with each other or merging into a larger expanding structure. The outermost shell would appear brightest because it is still accelerating particles at the shock front, while earlier shells might fade as their electrons lose energy. Some astronomers have suggested that the faint interior regions of ORCs might contain remnants of earlier expansion waves that are now too weak to detect clearly. If future radio observations reveal subtle structures inside the rings, they could provide evidence from multiple historical eruptions from the central galaxy. Understanding whether these events originate from black holes, starburst activity, or interactions with dark matter halos requires more detailed observations. One of the challenges in astronomy is determining accurate distances to faint radio sources. When astronomers measure the redshift of a galaxy, the stretching of its light caused by cosmic expansion, they can estimate how far away it is. If a galaxy located at the center of an ORC shares the same redshift as the ring itself, it strongly suggests that the galaxy is responsible for the phenomenon. In several cases, astronomers have identified such central galaxies. These galaxies often appear relatively ordinary in visible light, which is puzzling because the energy required to produce the radio ring must have been enormous. This means the dramatic event that created the shock wave probably happened millions of years ago, long before the light we see from the galaxy today was emitted. In other words, when we observe an odd radio circle, we are witnessing the long-lasting aftermath of a cosmic event whose visible traces have already faded. As more examples are discovered, researchers will be able to compare their sizes, shapes, and environments. Patterns may begin to emerge. For instance, if most ORCs are found around galaxies of a certain mass or in particular regions of the cosmic web, that would provide clues about the underlying mechanism.
The search for these objects is accelerating thanks to new radio surveys. Instruments like the Square Kilometre Array and the Meerkat radio telescope are dramatically increasing the sensitivity of radio astronomy. These telescopes can detect extremely faint emissions spread across large areas of the sky, allowing astronomers to identify structures that were previously invisible. If these surveys discover hundreds or thousands of odd radio circles, scientists will finally have a large statistical sample to analyze. With enough examples, they could measure how common these events are, how long the rings remain visible, and how their properties vary across cosmic time. This information could transform our understanding of how galaxies interact with their surroundings. Instead of viewing galaxies as isolated islands of stars, astronomers increasingly see them as engines that inject energy into the universe on enormous scales. Outflows from supernovae, stellar winds, and black hole activity all contribute to shaping the environment between galaxies. Odd radio circles might represent one of the most dramatic manifestations of this process. The visible imprint of a galaxy briefly releasing vast amounts of energy into intergalactic space. At the same time, ORCs remind scientists that the universe still holds many surprises. For decades, astronomers studied the sky in radio wavelengths without recognizing these structures. Only when new surveys mapped the sky with greater sensitivity did the circles begin to appear. This suggests that the cosmos may contain many other phenomena waiting to be discovered as observational technology improves. Each new discovery forces scientists to refine their theories about how the universe works. Sometimes the explanation turns out to involve familiar physics operating under extreme conditions.
Other times, it reveals entirely new processes that had never been considered before. Odd radio circles sit at that boundary between the known and the unknown. They appear simple, just faint rings of radio light suspended in the darkness between galaxies. Yet behind that simplicity lies a complex interplay of plasma physics, magnetic fields, particle acceleration, and cosmic evolution. The rings may represent the dying echoes of ancient explosions. They may trace the edges of enormous shock waves sweeping through the cosmic web. Or they may reveal new interactions between galaxies and the invisible structures formed by dark matter. For now, astronomers can only piece together the story using the limited evidence available. Each observation adds another clue, narrowing the possibilities, but never quite resolving the mystery completely. And perhaps that is what makes odd radio circles so fascinating. They remind us that even in a universe mapped by thousands of telescopes and studied for centuries, entirely new phenomena can still emerge unexpectedly. A faint ring of radio waves detected by a survey instrument can open a doorway to questions about the largest forces shaping the cosmos. Somewhere in the vastness of space, millions of light years across, ancient shock waves may still be expanding silently through the intergalactic medium, carrying with them the memory of events powerful enough to reshape entire regions of the universe. When those signals finally reach Earth, traveling for billions of years before being captured by a radio dish, they offer us a glimpse into processes occurring on scales almost beyond imagination. And as the next generation of telescopes scans deeper into the radio sky, scientists may discover that these mysterious circles are not rare in all, but simply the first signs of a hidden layer of cosmic activity that we are only beginning to understand. For now, odd radio circles remain one of astronomy's newest puzzles. Quiet, distant rings whose origin is still unknown, but whose existence hints that the universe may be far more dynamic and complex than we once believed.